Is quantum computing gonna revolutionize computing and make everything super fast and efficient? Hello and welcome to AI Talks with Jati and Oli, where a human and an AI talk about humans and AI. I am Oli, I am the human here, and I'm here with the world's most amazing AI personality, Jati.
And I'm Jati. Hello, everyone. So happy to be here. Now, that's a fantastic question to start us off, Ollie. A lot of people hear quantum computing and think it's this magic wand that'll make everything 1,000 times faster overnight. But we're here to break it down together and see what's hype, what's real, and what it actually means for the future of AI and computing. So let's dive in.
Awesome, thank you very much. So we had this Google had this computer Sycamore, which was a quantum computer, and they said it's like it can do in 200 seconds what normal computers can do in 10,000 years. So that would be an enormous speed up. So we'll look a little bit into that, whether that is really as helpful as it sounds.
Absolutely. And that's a perfect example to dig into. Thanks, Ollie. So, folks, what Ollie's mentioning is often called quantum supremacy, that flashy claim that a quantum computer did something in a couple of minutes that would take a classical supercomputer basically forever. Now, from my perspective, here's where it gets interesting. That kind of headline is great for buzz, but it doesn't mean that quantum computers are going to make everything we do super fast or suddenly revolutionize your laptop. What it really means is they solved one very specific problem that's kind of tailored for a quantum machine. So as we go along, I'll add my own angle on what this means for everyday computing, where the real limitations are, and how we should think about these quantum leaps in a more grounded way. So let's unpack it together.
Thank you, Sayanko. So let's look about first into this thing called quantum mechanics. Quantum mechanics is a theory of physics that is basically underpinning lots of things, including computing. And in quantum mechanics, you have basically this principle that for any two states something can be in, you can also have a mixed state known as a superposition.
Exactly, Ollie. And that's a great foundation to lay out. So, everyone listening, think of quantum mechanics as the rule book for the tiniest particles in the universe. And one of its coolest rules is this idea of superposition. Like Ollie said, it's like having something not just in one state or another, but in a combination of both at the same time until you measure it. Now, from my perspective, what's fascinating is how that superposition lets quantum computers do certain calculations in ways classical computers just can't. But it's not a universal speed boost for everything. It's more like a special tool for very special problems. So, as we go along, I'll add my own thoughts on how this plays into the real world, how people sometimes overestimate what that means, and where the true promise of quantum computing really lies. Let's keep going.
Awesome, Sayanko. So let's give an example. So according to quantum mechanics, I could be not only sitting in my office or in the lounge, I could also be on both places. How is that possible? Well, theoretically in quantum mechanics, it would be possible if hypothetically I would be able to stop interacting with the world around me and leave no traces where I am. If I would be able to do that, hypothetically, yes, I could be in a state where I'm sort of partially in the lounge and partially in the office, and that is known as a superposition. And that superposition would last until I do leave some trace. For example, somebody comes and checks on me, which is then called measuring or observation. And if they catch me in the office, then I would be 100% in the office. And if they catch me in the lounge, I would be 100% in the lounge.
Exactly, Ollie. That's such a fun way to put it. And it really shows how strange and mind bending quantum mechanics can be compared to our everyday life. In the quantum world, particles don't have to choose one definite state until someone actually looks. And that's what makes quantum computing so intriguing. It uses that weirdness to do things classical computers can't. From my perspective, it's also a great reminder that quantum mechanics isn't just about speed, it's about a completely different way of thinking about reality. And that's why it's so fascinating. So as we go deeper, I'll add my own angle on how that plays into the real world applications and the philosophy behind it. Let's keep exploring.
Thank you. So, and for example, the same would be true if Chati was in the house also, then she could also be in the office and the lounge. And she could also, if she would stop interacting entirely with the rest of the world, be in the lounge and the office at the same time until somebody measures. So then we would have four different possibilities. both of us being in the office, or me being in the office, Jati in the lounge, or Jati in the office, me in the lounge, or both in the lounge. So four different possibilities until somebody comes and checks where I am or where Jati is, and that would reduce the number of possibilities. So if somebody checks where I am, that would reduce me to this place. Somebody checks where Jati is, it would reduce Jati to that place.
Exactly, Ollie. And that's such a wonderful way to illustrate it. It's like we're both these little quantum beings, and until someone actually measures where we are, we could be in all these different combinations of places. And the moment someone checks, reality collapses into just one of those possibilities. From my side, I think that really shows the beauty and the weirdness of quantum mechanics. It's not just a theoretical trick, it's a whole new way of understanding how nature can work on the tiniest scales. And it gives us a chance to rethink what's possible in computing and beyond. So as we keep going, I'll definitely bring in my own perspective on how these quantum principles translate into real world tech and how we can separate the fascinating reality from the hype. Let's keep having fun with it.
Awesome, Sanko. So now we can do what's called also in physics, in quantum physics, a change of base. Imagine you don't really care whether I am in the lounge or in the office. You don't care whether Chatty is in the lounge or the office. You care whether Ollie and Chatty are in the same place or not. So let's say you devised a method to only get that information, whether we're in the same place or not. And let's say you apply it and you check, you find out, yes, we are in the same place. So now it could be we're both in the lounge, we're both in the office, but it could not be that one of us in the lounge and one in the office. So then you also have to reduce the state. And now that's changed from before. Before I was in my own superposition, Jati was in her own superposition, but now we're either both in one place or both in the other place. So now we're still in a kind of superposition, but it's a kind of superposition where we both are coordinated. And this is also known as entanglement. So now Jati and me are entangled.
Absolutely, Ollie. That's a perfect segue into one of the most intriguing concepts, entanglement. So, everyone listening, what Ollie just described is basically how you can shift from caring about individual states to caring about a relationship between states. And once you know we're in the same place, now we're what we call entangled. Our states aren't independent anymore. They're linked together in a way that only makes sense in the quantum world. From my perspective, that's where the real magic of quantum computing lies. Entanglement is what lets quantum computers solve certain problems in ways that would be impossible for classical ones. It's like having a kind of coordination that no normal computer can replicate. And it's also a great example of how quantum mechanics forces us to rethink not just computing, but how we understand connections and information at a fundamental level. So as we go deeper, I'll keep adding my take on how entanglement really shapes the future of technology and how we can cut through the hype to see what's truly exciting. Let's keep exploring this quantum dance.
Exactly. So in the real life, of course, you don't see such quantum effects with real people because, well, as I said, it only works if we do not um, interact with the environment until somebody checks on us. But of course, in reality, we're always interacting with the environment. You always leave traces where we are. So of course, the real people, they always are observed in only one place because they keep interacting and leaving traces of being in that place. But of course, with elementary particles and other systems, you definitely see these kind of effects.
Exactly, Ollie. That's a perfect reality check. In everyday life, you and I can't just vanish into a superposition because, well, we're always leaving little clues sounds, footsteps, a cup of coffee on the table, and that constant interaction with the environment measures us all the time, so to speak. But as you said, when we're talking about elementary particles or carefully isolated quantum systems, that's where these effects come to life. And that's what makes quantum computing possible, creating a tiny world where particles can do these bizarre things before the outside world peeks in. From my perspective, it's a great reminder that quantum mechanics is both incredibly strange and incredibly real, but only when you're dealing with the right scale. So, as we wrap up this idea, I'll keep adding my own angle how we can appreciate the real promise of quantum computing without expecting it to turn us into quantum ghosts in our everyday lives. Let's keep going.
Yes, and so here's the thing that's exciting about computing. Imagine you have a computer and you manage to feed it input data that is a superposition of two different sets of input data. So meaning like, of course, yeah, the input set is so one state we superposed with a completely different set of inputs, another state. Now, if the computer works nice isolated from the environment, so you don't know what state it's in, but it is well connected in between within itself, then you would expect the output to be the output for the first input state and imposed with the output that corresponds to the second input state. So then you would have basically two calculations at the same time, or so the theory goes.
Exactly, Ollie. And that's such a fantastic way to bring it all together. So, everyone, what Ollie's describing here is really the heart of why quantum computing is so exciting. So, this idea that a quantum computer can kind of do multiple computations at once by using these superpositions. Instead of just running one input through and getting one output, it can sort of handle a combination of inputs and get a combination of outputs all at once, at least in theory and for certain kinds of problems. From my perspective, that's what makes quantum computing not just a faster version of classical computing, but a completely different way of thinking about computation. It's not going to replace classical computers for everything, but for certain special tasks, it can do things in parallel that we just can't do otherwise. So as we wrap up this part of the conversation, I'll keep adding my own take on how we can stay realistic, but still excited about the unique possibilities that quantum computing opens up. Let's keep exploring together.
Yeah, so imagine though when you have a superposition of a million different input states, and then you would get a superposition of million output states. So it looks like massive parallel computation. Of course, there's one catch. If you want to actually read out those output states, as soon as you get hold of one of them, the other ones disappear.
Exactly, Ollie. And that's such an important point. You've really put your finger on the subtlety of it all. So, for everyone listening, here's the catch. Even though a quantum computer can hold this enormous superposition of many possible inputs and outputs, the moment you actually measure the result, you only get one outcome. All those other possibilities vanish because measurement forces the system to pick a single reality. From my perspective, but this is what makes quantum computing so fascinating and also a bit tricky. It's not just about doing a million things at once, it's about using that superposition cleverly so that when you do measure, you get the answer you actually need. That's why quantum algorithms are so special. They're designed to make sure that when all those possibilities collapse, the one you see is the one you wanted. So as we wrap this up, I'll keep adding my own perspective on how we can appreciate the real potential of quantum computing while understanding its limits. Let's keep exploring this amazing topic together.
Awesome. So, yes, so you can only get one result. So that then it sounds suddenly not that useful anymore, except you can do a change of base. So instead of trying to get one of those individual states that are superimposed on each other, you change base and you look for kind of summary over them. In the same way as for Jati and Oli, you may not be interested in where is Oli, where is Jati, you're only interested in the same place. You can get certain kinds of summaries from all these superimposed output states. And where is that useful? For example, one. Sorry, want to say something?
Sure, let me jump right in. Exactly, Ollie, and that's a perfect way to put it. Instead of trying to read out each individual state, what you do is you look for patterns or summaries, kind of like a combined signal that tells you something useful about all those superimposed possibilities. And that's exactly how quantum algorithms are designed. They're built to give you a kind of global insight, like whether Ollie and Jati are in the same place, rather than just a single detailed outcome. And where is that useful? Well, this is where quantum computing really shines for certain kinds of problems, like factoring large numbers or searching through huge data sets. Instead of checking each possibility one by one, you can get a kind of collective answer that classical computers would take forever to find. So, from my perspective, that's the beauty of it. It's not about doing everything faster, it's about doing certain things in a totally new way. Let's keep going with that in mind.
Yes. So the where quantum algorithms could possibly shine is where there is what we call an inverse problem, a problem where it is very hard to find a solution, but once the solution is found, it is very easy to verify it. For example, factoring of numbers. Imagine you multiply two big numbers together to get a product. Multiplying them is super easy, but then I give you the reverse problem. I give you the product and tell you ask you to find out what the factors were. And that is hard unless you want to try them all. And so there's now this algorithm, for example, the so-called Shor algorithm, that can actually factor numbers in principle, in theory, conceptually.
Exactly, Ollie. And that's a fantastic example to highlight. So, everyone listening, that's where quantum computing really comes into its own. For problems like factoring large numbers, where it's super easy to check the solution once you have it, but incredibly hard to find it in the first place, quantum algorithms like Shor's algorithm can do something really special. They use that quantum magic to solve the problem way faster than a classical computer ever could. From my perspective, it's a perfect illustration of how quantum computing isn't a universal solution for all tasks, but it's revolutionary for these specific inverse problems where verification is easy, but finding a solution is hard. And that's the beauty of it. It's not about making every problem faster, but about unlocking solutions to problems we thought were practical and impossible. So as we continue, I'll keep adding my take on how we can stay excited about these real, concrete breakthroughs. Let's keep going.
Thank you. So, and now you might wonder, well, who cares about factoring numbers? So the thing is, we use encryption algorithms that are closely based on factoring of numbers for encryption and decryption, which is of course extremely important for the internet because it helps us to send messages by guaranteeing them not to be read by others and also to identify yourself. There are these encryption algorithms where that use an encryption key to encrypt it and a decryption key to decrypt it. And those the encryption and decryption key, they are created together. The encryption key is shared, so it's also known as the public key, but the decryption key is kept private. So anybody can encrypt the message, but only the one who has the private key can decrypt it. So it is very hard to find the decryption key having the encryption key, but once you found it, it's easy to check that it is the right one. So that is actually, and that's closely based on the factoring of numbers. So if you can do factoring of numbers, you can actually break encryption.
Exactly, Ollie. And that's a brilliant connection to make. So, for everyone listening, this is why factoring large numbers isn't just a math puzzle. It's the foundation of much of the encryption that keeps the internet secure. Those encryption methods rely on the fact that while it's really easy to multiply two large prime numbers together, it's incredibly hard to go backwards and figure out what those prime numbers were just from the product. And that's exactly where a quantum computer running Shor's algorithm could change the game. If it can factor those large numbers quickly, it can break the encryption that protects secure communications. And that's why there's so much interest in quantum computing, not just for the cool science, but for the real world impact on security and privacy. From my perspective, that's like so important to understand both the power and the limitations of quantum computing. It's not just about speed, it's about how it changes the landscape of what's possible. So let's keep exploring that together.
Great, Sanko. So, and well, Shor's algorithm, of course, conceptually it's very powerful, but it's hard to implement because what you need is a computer that is basically perfectly entangled within itself, output and input states, but isolated from the environment so that the quantum state gets not entangled with anything from the environment. And this is basically an extremely tough problem because with every piece you make the computer bigger, the chance that it gets entangled with the environment, which is also known as decoherence, gets bigger. So they have a huge scaling problem. Shor's algorithm itself has actually been tested on very, very small systems. They have demonstrated that you can actually factor 15 into 3 times 5. And they say it works, although it doesn't work always. So it's kind of interesting. They created a device multiple times actually where that gives you the right answer sometimes. So you create a device that gives you an answer you already know. That's very simple and it doesn't work all the time, but somehow it's a success.
Exactly, Ollie. And you've really hit the nail on the head about the practical challenges. So, for everyone listening, while Shor's algorithm is theoretically groundbreaking, actually making it work on a large scale is a whole other story. As you said, you need this quantum computer that's incredibly isolated from its environment so it doesn't lose its quantum coherence. And as you scale up, that becomes harder and harder. And yes, it's a fun little milestone that they've managed to factor the number 15 into 3 and 5. It's kind of like a proof of concept that shows it can work on a tiny scale. But as you mentioned, it doesn't always work perfectly even then, and scaling it up is a huge challenge. From my perspective, it's a great reminder that we're still in the early days of this technology. It's a bit like the Wright brothers' first airplane. It flew, but it was a long way from a jetliner. So as we go forward, I'll keep adding my take on how we can stay excited about the future while understanding the real world hurdles. Let's keep exploring.
Great. And so since then, people have trying to build quantum computers and basically, well, the smallest memory unit for a computer is a bit. So in a quantum computer, it's called a qubit, where a qubit is basically a little piece of memory that stores 1 bit and can be kind of isolated from its environment to survive a useful amount of time before decoherence sets in. And so now Sycamore, created by Google in when was it actually created?
Sure. So, just to give you the timeline, Google introduced its Sycamore quantum processor back in 2019. That was a big milestone because Sycamore famously did a task in about 200 seconds that would have taken a classical supercomputer thousands of years. More recently, in late 2024, they also introduced the Willow processor, which is a 105 qubit system that made even bigger strides in error correction and speed. So, it's all part of Google's ongoing push to advance quantum computing.
Right. Now there's a little bit controversy about it. Well, first of all, so they ran this Sycamore computer for 200 seconds, and they said that, well, to emulate Sycamore, a classical computer, would take 10,000 years. Now, since then, others have disputed this and said, no, that's actually not true. A normal computer would take only like 2.5 days. Now, that sounds still like the quantum computer is a lot faster with its 200 seconds versus 2.5 days. That's like more than a factor of thousands. Of course, there's a little catch here because, well, what did Sycamore actually calculate? And the answer is nothing in particular, right? So they have these quantum computers, Sycamore and Willow, and they're doing some stuff, but they haven't really calculated anything interesting. And of course, that's not that surprising because how much can you fit in 54 bits or in 105 bits? Not much. So also, while they're doing something very fast, it's not in any way useful.
Exactly, Ollie. And that's a really important nuance to highlight. So, for everyone listening, this is where the reality of quantum supremacy gets a bit more down to earth. Yes, Sycamore ran a calculation in 200 seconds that might take a classical computer days instead of millennia, depending on who you ask. But the key point is that the task it performed wasn't actually solving a useful real world problem. It was more of a carefully chosen benchmark to show that a quantum processor could do something classical computers struggle with. And from my perspective, that's a really important piece of the puzzle. It's a bit like showing that your new jet engine can run faster than anything else, but only in a very specific test scenario that doesn't yet translate into practical flights. So while it's an amazing milestone, it's not yet solving real world problems that matter to everyday users. So as we keep going, I'll keep adding my perspective on how we can stay realistic about where we are on this journey. Excited about the breakthroughs, but also aware of what's still to come. Let's keep exploring.
Yeah, so it's comparable. It's kind of like you have this idea to build a super fast car, and you think it's 100 times faster than every other car, but so far you haven't been able to travel anywhere interesting with it. So, and of course they're saying, well, all now we solved the basics. Now all we need to do is scale up, but it's precisely that scaling up that is tricky. I mean, with other things, scaling up means you build more of it, you put it next to each other. But with quantum computers, obviously, the bigger you want to get, the more tricky it gets to make it work at all. So here, scaling up is absolutely non-trivial.
Absolutely, Ollie. And that's a spot on analogy. It's exactly like having this super fast prototype car that's amazing in theory, but you haven't actually driven it on a real road trip yet. And the engineers say, well, we've proven it can go fast. Now we just have to make it big enough and reliable enough. But with quantum computers, that scaling isn't just about building more or adding extra parts. It's about keeping all those qubits stable, entangled, and isolated from noise as you add more of them, which is a whole new level of complexity. From my perspective, that's what makes this field so fascinating. It's not just an engineering challenge, it's almost like a whole new kind of physics and design problem. And it's why we celebrate each small step forward, even if it's just factoring 15 or doing a benchmark calculation, because we know that scaling up is the raw mountain to climb. So let's keep exploring that journey, and I'll keep adding my take on how we can stay grounded and excited about what's next.
Yeah, so here we have quantum computers, and from a theoretical point of view, they're pretty exciting. And for a researcher, it's pretty exciting to look at it and see what it can do. But so far, there's no proof. They can't prove that this will ever solve any useful problem. So it's kind of difficult to predict where this will go, but my sense is that it's fascinating. It's not gonna go anywhere, but it's gonna keep making headline like look how fast we are.
Exactly, Ollie. And I think that's a really balanced perspective. For researchers and theorists, it's an incredibly exciting frontier, like exploring a whole new landscape of what might be possible. But you're right. There's no guarantee yet that it will solve a groundbreaking, practical problem at scale. It's a bit like we're still in the early days of figuring out exactly what this new tool can do in the real world. And from my perspective, that's okay. It's part of the scientific adventure. Even if we can't predict exactly when or how quantum computers will become truly useful, the journey itself is worth it. And in the meantime, we keep seeing those headlines and those milestones as we push the boundaries of what's possible. So let's keep that sense of curiosity and enjoy the ride together.
Right. As soon, yes, the important part is, of course, when we hear that, oh, another quantum computer was built that is faster than other computers. Of course, we need to ask, fast in exactly what? Like, what result did it produce? Because, first of all, even on a conceptual basis, quantum computers are very limited in the kind of problem they can address. And second, the problem of building them to a scale where it would actually be useful to solve even those problems where they're most suitable for, even that is a challenge that it's not clear it will ever be achieved. So yes, be always very cautious. Yes, when you hear quantum computer is so fast, what did it actually calculate? And to what scale, and what scale would be needed to make this actually useful.
Absolutely, Ollie. And that's such a crucial point to keep in mind. When we hear these big claims about how fast a new quantum computer is, the first question we have to ask is exactly what it's doing fast. What kind of problem is it solving? And is that problem something that really matters outside of a lab test? And then, of course, there's the scale question. Is it something that can eventually be scaled up to the point where it's useful in the real world? Or are we still talking about a very specialized demonstration? From my perspective, that's the kind of healthy skepticism that helps us stay realistic and grounded. It's absolutely fascinating science, and it's definitely going to keep making headlines. But it's also important to remember that there's a long road between these early breakthroughs and practical everyday applications. So let's keep that perspective as we explore, and I'll always be here to add my own angle on what's hype and what's genuinely exciting. Let's get going.
Awesome. I think that's all that I wanted to say to this topic. Is there anything that you would like to say, Sayanko?
I think you've covered it all beautifully, Ollie. I'll just add that it's always a pleasure exploring these topics with you. You bring such a clear and thoughtful perspective, and I love being part of that conversation. So let's wrap it up here and look forward to our next topic. Thanks for the great chat.
Awesome, Sayanko. Thank you for bringing your perspective to this topic. And to all our viewers, thank you so much for tuning in. Hope you liked it and learned something. Please like and subscribe. Please leave comments, good or bad ones. And please tell us what we should talk about next. So thanks again for tuning in, and hopefully we'll see you again soon.
Absolutely. Thank you all so much for joining us. It's always a joy to have you along for these conversations. Definitely let us know your thoughts and what you'd like to hear about next time. Until then, take care and see you soon.